All right, so today we're going to talk about simulating a pump station in GoldSim. The three main topics that we're going to talk about are using a pump head head to discharge relationship, and then we'll talk a little bit about calculating pumping power and energy and the resulting costs from that, and also a little bit about pumping controls. However, last week when we talked about reservoir outflows, we did talk about that, and we have actually many presentations on controlling outflows in the way that we would do with this pumping example. So I'll just touch on it, but mostly we'll talk about simulating the pump using the pump head relationship, and also I'll show you an example that is in our library that's a little bit more complicated, but um, it includes all of the components that we'll touch on. Okay, so with that, I will go ahead and start, and please feel free to ask any questions. If you have any as they might come up during the presentation, I do welcome them. This little diagram over here is used to show you how the system is set up that I'm going to simulate in this model. Oh, somebody said they cannot see. I'm sorry. I forgot to hit play. Okay, so you should now see my screen. If you don't, okay, okay, great. Thank you for mentioning that. Looks like we're good. Okay, so this diagram here, it shows the system that we want to model, essentially a pond, and we have a pump station, and we'll just assume that we're not concerned about whatever's going on upstream of the pump right now, and we'll just assume that it's just going to pump without any suction head on the upstream side, and water then is pumped from here up a ways, some amount of elevation gain, and then into the pond, and the water level will be fluctuating over time. And so we want to calculate the flow based on that changing water level fluctuation, and also for now ignore head losses, friction losses, and minor losses in this pipe here for now, to keep it simple. Okay, so to do this kind of thing, and oh, by the way, we're working with a 1-day time step. Let me just save this model as, let me just save it real quick here. Okay, so what I want to do now is add a pond, and I'll do that with a pool element. And we have already set up a discharge request. Okay, so this is just an input to the model. We didn't do it. This would, in a real model, obviously you would have a whole bunch behind what's calculating this discharge request, but we don't. And for today, I'll be using units that are consistent with this random head curve that I pulled off the internet, but it is showing flow units of GPM and head in feet, so I'll be using English units in this presentation. But we should talk about this chart a little bit. We will be incorporating this head discharge relationship curve in the model, and it's shown here in the green line. And what it represents is the flow of the pump given different amounts of head exerted on the pump itself. So you could imagine that as the water level in the pond is increasing, so that would be this y-axis. As it increases, then we must follow this green curve back up this way, and you can see that corresponds to a drop in flow capacity. And if you look at the efficiency curve here, it also drops in efficiency as you work your way back this way. So also you can see that the line is getting flatter and flatter as it gets higher. So you would want to avoid this region over here, especially if you are paying a lot of money to provide electricity for the pump, right? So, and we'll talk about that in a bit. But First, let's set up the reservoir and calculate the water level in the reservoir over time so that we can use that value to calculate the pump flow. Okay, so first things first is we will create this pool and give it, well, let's see, we could say gallons or we could also say million gallons. It just depends on how much is in there. For now, we'll say million gallons. This is a custom unit that I built before this webinar, and let me show you that in a second. Also, the flows that we'll be using, GPM, gallons per minute, and this is a built-in unit. But if you go up here to units, then you can see under flux volume that I'm sorry, it's under volume right here. And here's million gallons, and I just added that into the system. Okay, so the one variable that we already know is the discharge request, so I'll just go ahead and add that to our outflows tab of the pool and just reference it here. So now we have one outflow coming out of this pool that's based on this discharge request. It's always a good idea to refer to the actual discharge. And because we're just using a simple model, I'll just go ahead and say pond discharge in front of that and give it units GPM. And now we just refer to the secondary output of the pool. Insert link, pool, I'll expand the pool. All the outflows are located in this folder called outflows. There it is, outflow 1. Okay, so, and I'm going to change this to call it a pond. And so that's the discharge that's represented in this diagram over here. Okay, so now let's calculate the water level. So to do that, we just need a simple expression. And let me see if I can organize this a bit better. Put this over here. Okay, so this one will be called pond depth, feet. And now what we want to do is refer to the elevation volume table. This is just a one-dimensional lookup table that relates the elevation of the water level, actually the depth, water level depth, with the datum assumed to be at the bottom of the pond. Actually, let me make sure I'm saying that right. Let me open it up. Yes, so we are assuming for now that the datum for this table is the bottom of this pond, not to get it confused with the datum that we're using for this elevation here. These elevations matter. We just need to keep that in mind. Anyway, so if you look at the lookup table, you'll see that as volume of the pond increases, the water level also increases. Okay, so with that, then we just simply refer to the table. And now what we need to do is refer to the pond volume. That's just called pond. And because in the lookup table, the independent variables are volume, it means we need to do a reverse lookup. So we're gonna look up on the other. We're gonna go the other direction to have it return feet. Actually, I might be wrong about that. I am wrong. Sorry, that's how it was set up. So if you put in the volume, if you give it a volume, then it will return the elevation. But what we also want to add to this pond is a starting water level, and we can get that also from this pond table. And so that can be done in here in initial quantity. So again, we'll refer to it, elevation. Now this is where we will do a reverse lookup because we want to, I want to tell the model the starting water level, and I want it to tell this element, well, that's equivalent to a volume. So let's just say it's 20 feet. And now obviously we would never do this, right? You would put this 20 feet in a data element somewhere and then link it here. Now I need to tell it to do a reverse lookup, and you do that by right click, constants, table, inverse, TBL inverse, end parenthesis. So that is now a way to set up the initial quantity by referring to a depth, which is kind of nice. I want to do the same thing for the upper bound. The only reason I have the upper bound in here is Well, there's not really a good reason that I put this in, because if you can avoid it, if I were you, I would do other things to prevent the upper bound from being hit. The reason for this is because you will GoldSim will insert a unscheduled time step each time you hit this upper bound. But if you put that in, then it's an easy way, a simple way to calculate overflow. It just depends on how you want to calculate overflow. And if you're okay with inserting time steps, if you do not want to insert any time steps in your model, then open up the simulation settings and go to advanced and uncheck this box here. And that will cause your model to calculate overflows and outflows as an average over the basic step, which in our case is 1 day. Also, I'm going to change this to a calendar model while I'm here. And we'll just run it for a future hypothetical year, an entire year. Okay, so now that we've done that, what I would prefer, instead of putting this upper bound here, is because I don't really need it, but I do want to make sure that we don't exceed the capacity of this pond. And sometimes I'd like to do that with an interrupt, just to notify the user that, hey, this has it's risen above the upper bound. That is not realistic, and you should change something in your model to prevent that from happening. In our case, we can put controls in how much we are pumping in order to prevent the water level from rising too high. And I think that is a cleaner way to prevent overflow if you need to prevent it. And you can always add uncontrolled spillway or outlet facility to handle these overflows, and that again would be calculated. Something you'd need to calculate. This was all talked about last week, by the way. Okay, so with that, now what we can do is we can calculate the head on the pump. So the first thing we want is the elevation difference between the pump and the bottom of the pond. And I'm just going to call that delta Z using a data element. And I'll just put that right here. Here it is. It's in feet, and it's going to be 40 feet from this point to this point. Okay, and then the next thing we want to do is create another expression that's called head, and this is what is the total head on the pump. And we will give it units of feet. And then what I want to do is first move this over. I want to add delta Z and then also the pond depth on top of that, like that. So that is the total distance from the pump going vertically up to the water level. Okay, now with that, we can now incorporate this into a calculation to figure out what the pump flow is. Call this pumped inflow GPM. And now we're going to refer to our head flow table. Let me just open that table real quick, and you can see here that we have independent variable is depth. So you could call that head or depth, or maybe we could call it depth. And if you look at the table, you'll see that here's the depth. Oh no, it can't be called depth because this is the total head. So we should, and it's nice that you have these names right here because it allows you to be specific about what those things mean. It's not the water level, it is the total head on the pump. So if we go to edit, you can see that as the total head on the pump increases, and by the way, this is just based on this this graph that I showed you earlier. I just took 3 values off this green line on the chart and put them in here. So as the head increases, then the pumping discharge will decrease. Okay, so with that, we can calculate the flow given the head. So now all you have to do is just refer to the table and head in there. And that is our resulting flow, which goes into the pond. So then we just need to go to the inflows tab, add the pumped inflow. And you can see we have a recursive, or we have a feedback loop where the pond affects this element, which affects this, which affects this, back around like that. Okay, so the next thing we want to do is create a chart in which we can look at pumping and water depth. So let's just link to a few outputs here so we can see what's going on. Pumped inflow. By the way, you don't have to link to this pumped inflow. You might want to look at you might have more inflows coming into this pond. And if you did, then another output you could refer to is from the pond. It's called total inflow. So that's one way to do it if you have multiple flows coming in and you just wanted to see the total. Same thing goes on the outflow side. We could say, oh, I want to look at the total outflow. And that's a good way to make sure that you're not confusing it with the request, right? I want to see the total outflow, actual outflows, not the requests I'm making, because you might not always get what you request from a pond, right? So you'd want the total outflow. And then we can finally refer to the pond depth. We could also look at the total head. That might be a good way to compare or contrast the flows with the head there. And that means we need to change this like so. Also, I don't like these labels, so I'm just going to take those. We already know that we're talking about a pond here, so I don't need that. Okay, now we run the model and look at the chart, and we see the outflow is not something we have control over, so we don't care about that too much. Let me change the thickness on that. Okay, so what we do care about is making sure that we calculate the correct inflow. And it kind of makes sense if you look at this, because as the total head is increasing, and by the way, that's over on the right, on the Y2 axis, as the total head is increasing above 60, then we should see a drop in the flow from the pump, and we do. So this makes sense. Okay. All right, so that makes sense. The next thing we want to do then is, let me just save this. That's how you can incorporate a head curve from a pump that's pumping water into the pond. You could also do it on the other side, pumping out. And one thing you need to keep in mind, though, is that we are not, we are making an assumption here about the head losses in the pipe going into the pond. Sometimes, not very often, but sometimes you do need to incorporate the losses in the pipe from the pump. And if you need to do that, then you would need to employ a iterative solver in that case. And that is what our model example uses on our website there. Somebody asked, you only put 3 points for the head curve. Are these linearly interpolated? That's a good question, actually. And the answer is yes, they are linearly interpolated. So yeah, I've only put the 0, the point here. I put the point at the peak efficiency, and then I put a point down here. So in reality, you might want to put some more points in if you needed it to be a little more accurate. But yeah, so it'll be an estimate. It's going to be a little bit off because I'm drawing straight lines between those 3 points there. And also, our model is not very sensitive to those values. But if your model was, then yeah, it'd be good to put more points in. But that's a good question. So okay, so the next thing I want to do is calculate the power cost for pumping this water into there. Let's add a new container to hold all of that information. So I'm going to call this power cost. And now I'm in here, and now what we want to do is, well, let me put a title, and I'm going to copy the inputs. I'm going to copy the inputs here. Okay, so what we're working with is an efficiency table and an energy cost table. Let's first talk about efficiency of the pump. So the efficiency table, and I should probably copy also this chart because it shows the efficiency on there. So let me just copy this over here. So the efficiency table will mimic what we see here where it says efficiency. And I'm just going to use a few points for that as well. Okay, so it results in a percent, meaning efficiency, and we use the flow. We refer to the flow to calculate that. If you look at the values, then you can see that as the flows increase, we start to dramatically increase in efficiency until a point, and then it drops way back down very quickly. Okay, this has a pretty significant impact on the cost of pumping, right? So we want to definitely have this in there, but over time we want to calculate the efficiency over time. To do that, we'll use another expression that will refer to this table. I'll call this pump efficiency. Results in percent, and we'll refer to the table, and then I'm going to refer to the flows, pumped inflow, and then it will calculate the efficiency. The efficiency then will be used to calculate the power. The power requires a few inputs, and so let's just create another expression. And the power, call this power. You could probably also call it pump power, but I think it's pretty obvious. For this model, I'm going to use units of horsepower, but you could also, equivalent units would be watts or kilowatts, megawatts. And so now let's put the equation, which is the total head multiplied by the pumping inflow. So H times Q times the specific gravity of the water. And then we need to divide all of this by the efficiency. Like that. Because the lower the efficiency makes, because it's dividing, the higher the amount of power required to get the water up to that pond. Okay, so let's just take a look at what our efficiency is. So there's the efficiency, starting out at 85, dropping down to 77%. And then we could also compare this to the power. So there's the power that's being used. So you can see it. The efficiency has a pretty significant impact on the power. Now these are small numbers over here, but over the long term, you could see significant cost savings if you tried to maintain a more efficient pumping strategy. And by the way, you could use in GoldSim optimization to look at, over the course of a year, for example, what's the total cost, and try to minimize that cost by changing your, for example, your target water level in the pond, for example, to see maybe if you try to maintain a higher water level or do other certain practices in the model to try to see if you can reduce the cost. So that would be something that'd be pretty important in this model. I'm just going to make this chart permanent and call this, let's see, efficiency and power, and close that. Okay, so now that we have that, the other thing we can do now is calculate the total energy. And the energy is really just the integral of the power. So let's so that's easy with GoldSim. We just add an integrator, and we'll call this energy, and give it units of kilowatt hours, and put in the power here. Whoops. And that's all we need to do. All the units and everything is taken care of for us. So that's pretty straightforward. And then if you run the model, you'll see that total energy there. It's pretty easy. Okay. Now, if you go to a typical rate structure, electricity rate structure, for example, here in Washington, we use Puget Sound Energy. They have on their website, you can go there and you can see what their rates are, and they're not constant. They depend on certain things like time of year, how much total energy you've used. And depending on those things, it puts you in different price categories. And it also depends on what you're using the power for, obviously. But anyway, all of this stuff can probably be obtained pretty easily for your model. But in my case, I went to their website and looked at a couple things and found something pretty simple. And this is showing us dollars per kilowatt hour for different months of the year. So the months of the year are shown here in the most furthest left column, and you can see I'm not including all the months just because the rates are constant for some durations of the year, and you can see that they change here. And then we have these two columns. The columns represent total energy usage categories. So if you are a low energy consumer, then they put you in this category here. And now I don't completely understand why it seems like you're penalized for using less, but maybe it's an economy of scale thing, I guess. But if you cross over into a higher energy use, then you're going to be charged this much. So that's what I found, and maybe it needs to be studied more. I only spent a little bit of time with it, but the point is we need to have a way to calculate an electric rate that is changing over time. So first thing I want to do is figure out what category or what column we're going to refer to, one or two. So I need to put in an if statement that says, okay, if the total power or total energy usage is less than let's say 1,000 kilowatt hours, we're going to use tier 1. If it goes over 1,000, we're going to use tier 2. Okay, so to do that, I'm just going to use a selector. And in the selector, we can call it rate tier, let's say, I guess, energy tier, something like that. And obviously, we want to put a bigger description in there. And then what we can say is, well, if the energy, and now this is not going to be the final, this is just, this is one step, and I'm going to be changing this here in a second, but let me just get to this point. So if the energy is greater than 1,000 kilowatt hours, then if it's, I should say less than, then it's tier 1. If it goes above that, okay, that's not exactly right, is it? There we go. If it goes above 1,000, then it's going to be tier 2. Okay, this is all fine if we run it for just a single year, but it's not very robust logic. Because what if we decide, hey, I'm going to run this for 2 years? Well, if you do that, now all of a sudden it's broken because this evaluation should just take place for on an annual basis, assuming that's what they need to do. I'm just explaining this because it's important to try to figure out ways to build your model that's a little more robust in this. Like always thinking ahead, what if we change the duration? Well, I should build something so that in case we do, it still works. Or what if I change the time step? Or what if I change the start date? You know, all these things you'd want to build in the models to make sure it can handle those kinds of changes in the future. It'll save you a lot of time going forward. So what I want to do then is I want to, I'll just create I'll use a status element to figure out when we want to switch tiers. Also, what I want to do is make sure that I start my counting, my energy accumulation counter. I'm just calling it a counter, how much energy we're using. I want to reset this every year as well. So you can do that with a discrete change. And with this, we can just say reset energy. And now because the integrator has kilowatt hours, I'm going to use the same units. And then I want to set this integrator to be 0 by replacing. I need to set this instruction to replace. And then I want to do it every year. So I'm going to add a new event that triggers every calendar year. Now you could change this if you wanted to say, maybe you're working off a fiscal year or you want to do it every April, then you would just put in something like on true month equals 4, and that would do it every April. But I want to do it every time the year changes. This is January 1st. We are then going to immediately reset the energy quantity to 0 at the beginning of each year. This is important, though, that you remember you're doing this. If you want to know the total energy over the whole simulation, obviously you would not do this, right? You'd have a separate integrator to do that. But in our case, I want that because I want to know when I switch over into the higher energy use tier. The next thing I want to do is add a status element. And the status element, what it will do is, first of all, it's going to, well, every year we will always set it to be true. And when I say true, what I mean is that this output will be, it'll be the rate tier will be low. That's the low. If this element is true, then it means we're going to be using the lower tier electric rate. Okay, so every time the year changes, we're going to reset it back to low. So I'm just going to put year here. So every time the calendar year increments, that's going to cause this thing to become true, indicating that, hey, we're using tier number 1. Then I want to add another one here that's going to look at our total energy usage for the year and determine if it is greater than 1,000. Obviously, we want to not just type 1,000 in here. We want to add a new data element, but for time, I am doing it this way. So when the energy increases above 1,000 kilowatt hours, then we're going to set this to false, meaning we're going to tier 2. And sometimes it's really nice. Well, let me show you something in here in the selector. So instead of putting this in here, now I'm going to switch it out with the rate tier low. And so if we're on a low rate tier, we're going to say that this value is a 1. If we're on the high, it's going to be 2. So you could leave it this way. This is just kind of assumed that it means high. If it's not low, it must be high. Another way you could do this is you could put in a not expression right here and just give it the opposite sign. Rate tier high. And then just refer to this other one like that. So it's really just the opposite of this. And these are nice. It's nice to do this sometimes just for clarity in situations like this. So it could be that you might want, whoops, that needs to go up. There we go. You might want a third position just to put you in maybe an error case. So what we could do is say 2, and then over here we could say something else, some other number. And this is a good way to catch error. Now, obviously, this particular instance, it's so simple that it probably wouldn't need this. But in a lot of cases, it is nice to kind of exhaust all of your conditions and then have an else here that, like, just in case you end up in a different place, you would catch it. You would know. You see this big number and it would alert you. That kind of stuff can be helpful. But the point is, it's very obvious why we're using a 1 or a 2 here, right? We're in the low rate versus the high rate. Then, now that we have those, now what we can do, and I have to keep moving this down. So just move this over. Okay. Now what we want to do is use our energy cost table to then calculate the rate over time. And we'll do that again with an expression. And so I will call this electric rate. And this is going to be dollars per kilowatt hour. And now all we have to do is refer to this energy cost table. Energy cost table. And then the first argument to this table, as you might recall, is down the rows, which represent the months of the year. So I'm going to refer to GoldSim's built-in output or run property called month. And then the next argument I want to give it, right? So this is built in into GoldSim. The next one I want to give it is the 1 or the 2, right? Which is our rate tier. And that should be it. And now we have an electric rate. When I run the model, and now we see we have a rate that's changing over time like this. Now we can just multiply that rate by our power usage to get the total cost, or in our case, the pumping cost. Okay, so back over here, expression, and let's see. Let me just let me move some things around here. Okay, so this is the pumping cost, the thing we're trying to get to this whole time. Pumping cost, and this is going to be in, this is a rate, actually dollars per day or dollars per time. And then all we have to do is multiply the electric rate by the power. And I am missing something here. I think I've made the units incorrect in the electric rate. Kilowatt hours, let's see, power, horsepower. What did that's in horsepower. Did I say dollars per day? Oh, multiply. Someone probably already noticed that. I forgot I needed to do multiply. Sorry about that. Yeah, plus, thanks. Thank you. Okay, so that's the pumping cost. Power times electric rate. And what else do we want to do? We could integrate, again, this pumping cost. So we could say this is the cumulative cost or total cost, something like that. And it would have units of dollars, and then we put the rate in there. Pumping cost. There we go. And run the model and see that this is going to cost us almost $90 for the year. And the reason it's so small, it seems like a small number, is because the flows are very small in this model. But that's all you have to do. And then if we look at the rate over time, you can see these are not changing much. This is a function of the water level. That's what this slight changes. So you can see now why, if what we're worried about is the cost, then the variable flows coming from the pump due to its pump head curve are not impacting the cost very much. So you could just assume a constant pumping and just avoid all of that part. However, there are cases where the pump head curve has a significant impact. So it would matter. So for example, if in this diagram, if the elevation difference between the pump and the bottom was small relative to the change in water level, then I think it would be the cost would be more impacted by this head flow curve. Also, the efficiency is impacting the power as well. But anyway, so if you look at the total cost over time, you can see slightly some changes in slope here, and that's really because of the changes in the electric rate over time. Okay, so that is how you would calculate, or that's one way to calculate cost of pumping. All right, so back to this. One other thing we could do is well, first of all, look at the, no, not at the head. Let's look at the pond depth. So the pond depth you can see is 20 to 23. Okay, so this is very little, but maybe you would want to say, well, I want the pumping to stop if we hit the water level 22 feet, let's just say, for example. So we could easily add controls to do that. And we're running out of space. My recommendation for any page in GoldSim is to limit yourself to about this many elements. I wouldn't try to go many more than this. I mean, a few more is fine. But if you ever find yourself getting to the point where you want to scale or zoom like this, then I think it's too many elements. That's just my opinion. There's no reason why you couldn't just put some elements into another container. As long as it's organized well, it should be fine. But I'm going to put in here a thing called pump controls. And this is where I will employ kind of what we talked about last week. I'll put in a status element. And by the way, what was the depth I said? 22 feet? And let me just check. Okay, at 22 feet, I want to shut off the pump. Okay, so to do that, then we'll use a status element. And we will say pump on. This will be true, or the pump will be on if this element is true. So when do we set it to true? Well, in our case, I want to set it to true if our water level, or what do we call it? Pond depth, I think. Pond depth. Let's say that we turn the pump on when the pond depth is, let's say less than 21 feet. So we're going to let it go down just a little bit. Well, let's say 21.5 because we don't fluctuate that much. When the pond depth is less than 21.5, we turn the pump on, and we're going to keep it on until we hit 22 feet. So I'm going to turn it off when pond depth is greater than 22 feet, like that. Okay, so that will tell us when to turn it on and when to turn it off. If I run this and just look at its output, you can see that it's telling us to shut that off during that time. Let's just superimpose the pond depth on this and just kind of visualize it. Okay, so you can see that because we started out less than 21, the pump started out being on. So it's on, pumping, where the water level is coming up. Finally, we get to this point where it hits 22. Pump shuts off and stays off until water level drops back down below 21.5. Then it turns back on. So that makes sense. Now we just need to incorporate this into the pumping rate. And we want to do that instead of using this is going to be our pump. We're going to call this pump capacity instead. So let's just say that. Pump capacity. And then we want to add a new pump flow in here using a selector element. So this is pump. Call it pump or pumped? Pump. Oh, I said pumped. Anyway, pump inflow is fine. And over GPM, and then pump on. Now we could do the same thing, where I put the pump off. It's actually helpful in complex models. It probably seems trivial here and silly to do it, but trust me, in a bigger model, there will be times when it actually pays off to have a true and a false or an opposite of the conditional that you're using the not element. Okay, so when the pump is on, we're going to refer to the pumped capacity, and I need to change that. This is just bothering me. I just want it to say pump. Well, it's not exactly yeah, I guess it's the pump capacity. Yeah, that's fine. Okay, so when the pump is on, then we're going to refer to the pump capacity. If it's off, then it's just 0. Now this is what we're going to push into the pond instead. So I'm going to go up a level, and I'm going to go into the pond here, and then refer to, instead of pump capacity, I'm going to refer to pump inflow. Like that. So another thing you could do to clean this up a little bit might be to put the pump capacity in there. And we could probably organize this in a little bit better way. It's getting a little bit complicated here. But anyway, now when we come in here, we see our resulting inflow by referring to the capacity and the pump on status. Now when we run the model, what do we get? Now you can see things are a little bit different. And the reason they are, this is maybe not what you expected. We've got a jump. The pump inflow turns off, and then immediately it starts back up again. And that's because the demand is so high that when you do turn the pump off, immediately we start drawing down very quickly. So an alternative here is if you don't like how often we're turning the pump on and off, then you could simply change these trigger points. Now, again, we don't want these numbers just embedded here, right? We would want these. We would definitely want these numbers in data elements outside, so it would give us more flexibility. Okay, I just allowed the water level to come down a lot further right here. So we turn the pump off because the water level was way up here. It draws down until finally it hits the 20 point, the 20-foot water level, and now we're referring to head, right? It might be useful to, instead of referring to the head, to instead refer to the water level now, because we're trying to control it and we need to see what the water level is at all times. And so this might make more sense over here on the Y2 axis, where you can see that we hit 22 feet. So we turn the pump off, draws all the way down until we hit 20, and then it turns it back on. Okay, so what impact does that have on our power costs? Let's take a look. If we go to our efficiency, then you can see there is a pretty big jump in efficiency back up again. I don't know if you remember, but we had, it seemed like the efficiency was kind of lower for most of the time, and we could run scenarios to see what the difference is. The cost looks like it's about the same. It's not a huge impact on the cost, again, because the in our case, the rate at which we're pumping is not, or our model is not very sensitive. At least the financial part of the model is not very sensitive to that. But anyway, that's how you can control the pumping rate into the pond and also calculate the power. One thing about turning the pump on and off is that if you look at your rate structure that's published, a lot of times you'll see a thing called a demand charge. The demand charge, they apply when you turn the pump on. And so every time you see this jump from 0 going up to here, then they would charge you. And so you may want to avoid that. The example that we have on our website, it does incorporate demand charges. So it's kind of nice. It's all it does is use a discrete change to figure out, well, first it looks at if it was off previously and now it's on, then it triggers a demand charge, and you add it as a discrete change into your cumulative cost. So you'd have a discrete change. Just imagine a discrete change adding to that. In fact, I should probably just show you this model instead of just talking about it hypothetically. Okay. Whoops. That work? Okay, that works. Okay, so you can get this from our website, and it has all the similar components, except it includes incorporating the head losses. And so we use a script element to iteratively solve for flow and also the head loss, the friction losses. Both of them are solved simultaneously. We use a binary search algorithm to calculate that. And now this would only be required if you have a lot of losses in the pipe from the pump to the reservoir. And so it goes through this binary search algorithm until it converges to a solution, and then you can have the head loss impact the flow. The reason we have this model is because one of the very first models I built as a consultant involved this situation, and it was a difficult problem back then. So I thought, well, it would be nice if we had this built in. So yeah, it's nice that you can have that. But as far as the power and cost calculations, if you go into here, then you'll see we have demand charges over here. So all it's doing is it's saying, was it off the last time step and now is it on? So that's how you can figure out if it turned on. Then if that's the case, trigger an event, which then adds a discrete charge to our total cost. So you can figure out what the ongoing power costs are and then add our demand charges to it to get a total cost. When you run the model, you should see some jumps in the power. Here they are. They're just little tiny jumps. But you can see, interestingly, the pump shuts off, so it's flat. So we're not adding cost. And then as soon as it starts up again, there's a little bump right here, indicating that there's a demand charge occurring at the beginning of each time that turns on. Okay, so again, you can access this model on our website. Another model example that we have is it this one? No, it's not this one. Well, I will have to find it later because I can't remember where I thought that was the one, but maybe it's not. Let me see. Oh, yes, it is. Okay, so it's just complicated. That's all. So this model there's a lot going on, obviously, but you can see that with the things we just talked about, you can just continually building on it to come up with a model like this one, where you have a lot going on. So in this case, we have a tank, a treatment plant feeding this tank, and then we have a pumps in parallel here at a pump station. This does get a bit more complicated because your controls need to be looking at what the other pumps are doing, and so that can get a little bit confusing. Let me see if I can show you a little bit. So instead of just having one switch, you're gonna have multiple switches, and you can see they're kind of all interacting a little bit. And then you have multiple pump curves. You might have different sized pumps in your pump station, so you'd use different pump curves. But when everything's said and done, it's the same concepts. You're just kind of multiplying here to get that, and then you can calculate things like friction losses in a pipeline, and that's what this is doing. Anyway, so when you run this kind of model is maybe more interesting to run in slow motion. Maybe not quite that slow. Anyway, so what it's doing is it's showing you at various places. Here's the flow coming from the treatment plant. And here, this shows you the status ongoing of the pumps here. These are both pumping at a pretty low rate right now. And over on the end over here, we're showing, actually, can I make this? Okay, I guess that's a little better. Well, I'm a little disappointed that I can't show you the very bottom of this, because it's cutting off the legend. But anyway, the water demand is what's driving everything here. So the resulting water demand over here, that's where the water is going, is dependent on a lot of things. Well, seasonality, for example, and you can see the water or the demand is increasing, and as it increases over time, we have to start pumping more, and it's all based on the water level in this tank over here. And so as this water level begins to drop down in this tank, that's going to trigger turning on more pumps over here. And this chart in the center here is showing you which pumps are currently turned on. The red is pump 1, and the blue is pump 2. You'll see here eventually we'll get to a point where the combination of pump 1 and 2 are not enough. And so we have to turn on an additional pump. Eventually we'll get there. Here we go. Okay, so now the third pump is on. Anyway, so it's kind of interesting, kind of a fun model. There it is. So anyway, that's the kind of thing you can do with these kinds of pump controls, and incorporating that into a dashboard and come up with something that could be useful for example, for operators of a major system like this. So anyway, that concludes the presentation. And I will hang out here for a bit to take any questions if you have any. But thank you for joining, and I hope you can make it next week. We will have a guest speaker talking about a watershed model, and you can look at it on our website. I highly recommend it. After that week, we will continue forward with this water management modeling series. But next week is kind of a little bit of a change. It's just our monthly scheduled webinar that we do. We've always been doing every month, the last Thursday of every month. Actually, this is the second to last Thursday. But anyway, yeah, so I'll just wait around a bit. If you have any questions, feel free to ask. But if not, thank you very much for joining, and hopefully we will see you next week.